Hi, this is Professor Dickerson. In this video, we'll be learning about correlation. And I just wanted to make a note that a lot of this may be review if you covered correlation in Stat 1, but that this topic is going to be really important once we get to multiple regression. So I want to make sure that we're all experts at it before moving forward. Let me get my pointer here. And let's begin. So I'm going to be beginning all these videos with a list of learning objectives so that you can sort of stay focused on what's important for you to get out of each video. So I'm not going to read this slide for you, but the list is there for your reference. And then we'll return to it at the end of the video and make sure all these points make sense now that you have some context. Correlation and the next topic, simple linear regression, both deal with what we call bivariate data. So this is when each subject, whether it's a person or a state or a country, each subject has two different numeric variables measured. So this results in data that come in pairs where we have an X value and a Y value. Now, I want to distinguish that this is different from paired data that we've seen in the past. So let's see, we did an example a month or two ago where we looked at the sales of different sales representatives before and after a training. So we had a before and after pair situation, but it was the same variable, the number of sales before and after. Here we have two different variables, both numeric though. So let's say we're interested in how students do on an exam. So one of the variables is their exam score. And then we're going to look at the relationship to a couple other variables. So one might be how long they spent studying in hours. Okay. This is fictional data, by the way. All right. Another variable that might help explain their exam score is how many classes they were absent for. So we have those. And then a third variable would be each student's height in inches. All right, so if we graph these, well, maybe go ahead and make some predictions right now. What sort of relationship would you expect between the time someone spent studying and their score in an exam? You know, at least if they're doing a good job studying, one would expect that if they study more, they should score more points. Whereas if we count how many times they were absent, we would think that these students who were absent more would score less points, at least on average. And then over here, we might wonder, well, would there be any relationship at all between someone's height and their exam score? I mean, you could have tall people who do really well. Then again, you could have tall people who don't do very well. And the same for short people and people with intermediate heights. All right, so let's make some scatter plots. In just a moment, we will. So that's the first step whenever you have bivariate data is you want to make a scatter plot. So you're looking for the general pattern. Does it seem to form a somewhat linear trend, no trend, maybe a curved trend? So just a note, correlation, which we're doing today, and simple linear regression coming up in future videos are not appropriate for curvilinear relationships. So if you plot your scatter plot and see a curved pattern, there's some things we can do, but plain old correlation would not be one of them. Okay, so with correlation, we're going to measure the strength and the direction of the linear relationship between the two variables. With simple linear regression, we can do more things. We're going to use an explanatory variable or an X variable to predict the Y variable. And then we can do some fancy things associated with that, like test how the rate of change is between those two variables and more. But for correlation, this is pretty much descriptive. We're going to describe the relationship between the two variables. All right, so here are those three data sets where we're looking at the relationship between some X value, like say hours spent studying, and a Y value, which in this case is exam score. All right, so here we see a pretty clear linear trend. There's a little bit of scatter, but it's pretty clear that these sort of line up more or less. And the slope is increasing. So it seems that as the hours spent studying increase, the exam score tends to increase. As I predicted, over on our number of absences, as the number of absences increases, it looks like there's a pretty clear linear trend that the exam score goes down. And then over here with height, there's just a whole lot of random scatter. There doesn't seem to be any clear linear trend here. Okay. So these kind of exemplify the three directions of a relationship that we might see. If X increases and Y tends to increase, the general pattern is sloping upward, we would call that a positive relationship. Whereas if the linear trend slants downward, that is, as X increases, Y decreases, we would say that that's a negative relationship. And then if as X increases, Y doesn't really tend to do anything, go up or down, just a lot of scatter that's sort of evenly distributed across, then we'd say that there's no relationship. Okay, so the last slides were fictional data, but let's get to a couple real data sets. So my two main teaching examples for correlation and simple linear regression are going to be this gas stations data set and this muscle data set. All right, so the gas stations, our two variables are how much traffic is on a certain road, a road that a gas station is on, and then the sales of that gas station, how many thousands of gallons of gas that they sold. I should note traffic is in thousands here as well, but just multiply any of these numbers by 1,000 to get the realistic number. All right, so for instance, in row number one, these two numbers are lined up because that's a gas station where they had 33,600 vehicles passing by, and they sold 6,640 gallons of gas. All right, so would you expect, before we plot this, would you expect a positive relationship, negative relationship, or no relationship between these two variables? And once you think you have a guess at the direction, do you think it would be a strong relationship, like with the points really line up well, that there's a strong correlation between traffic and sales? Or do you think it would be maybe moderate or weak? Just take a guess. We'll find out in a moment. And then over here, we have a different data set. So we have, for a bunch of middle-aged and elderly men, their age in years, and the number of pounds of lean muscle mass. So this would be take your body weight and subtract out all the fat. So this includes both the muscle and the skeletal tissue, etc. All right, so positive, negative, or no relationship, and strong, moderate, or weak if you think that there is some kind of relationship. All right, so we'll be describing the strength of the relationship with what's called Pearson's correlation coefficient, symbolized little r. So here's the formula for little r. I'm not going to ask you to calculate it by hand. It's rather time consuming because there's a term in this sum for every value in the data set. But let me just point out a few important features here. So if you look at this part here with all the x's, what does that look like? We have a value minus the mean divided by a standard deviation, all pertaining to x. So that's a z-score for the x value. Then over here, we have the z-score for the y value. All right, so what do z-scores do? Remember, they standardize. So this is going to cause our correlation coefficient to be the same whether we measure traffic in thousands of vehicles or whether we measure it in number of vehicles. If we multiply by 1,000, it's not going to change our results any because these have been standardized. Okay. So what's going on in this formula? Well, we'd have our z-score for x multiplied by the z-score for y. Okay. And sorry about my little webcam. Oh, we can move it. All right. So if we have a value that's above average for X, it's going to have a positive z-score. If we have a value that's above average for Y, it'll have a positive z-score there as well. So you'd have a positive multiplied by a positive if you have points that are up here. What about values that are below average for both? Well, you'd have a negative times a negative down in quadrant 3. So if you have a positive pattern, most of your points are going to be in quadrants 1 and 3, resulting in a positive value for R. On the other hand, if you're in quadrant 2 or quadrant 4, one of your variables is above average and one is below. So you have a positive times a negative or a negative times a positive, and as a result, your correlation coefficient will be negative. So this is how we can, using a formula, pick up on a trend that may be immediately obvious by eye, whether the line is going up or the line is going down. But this formula doesn't have eyes, but it can still accomplish the same thing. All right. Another property of R is that this correlation coefficient is going to fall somewhere between -1 and +1. We cannot get any values that are beyond those bounds. And finally, because we're just multiplying the z-scores here, in multiplication, the order doesn't matter. So no matter which variable you're kind of thinking is X and which variable you're thinking is Y, it doesn't really matter, at least for correlation. It will become very important once we get to linear regression. Let's put them back over here. All right, so let's go to JMP. I'm gonna walk you through the gas stations example, and then you'll try the muscle example on your own. Let's see here. I'm trying to escape and it's not letting me. There we go. Okay, so I'm going to my gas stations. All right, so if you just want the correlation coefficient, you're going to go to Analyze, Multivariate Methods, and then Multivariate. And as my cursor is there, the little pop-up box says Correlations. And then, like I said, it doesn't really matter which variable is which. So we're actually going to pick both of them and assign both as Y. Press OK. So we'll get two scatter plots, one with the first variable as X and the other with the other variable as X. So here where it says traffic in thousands of vehicles, in the lower scatter plot, traffic is X. But in the upper scatter plot, traffic is Y. See how it kind of works with that square pattern? So down here, traffic is X, and these are the thousands of vehicles per day. Whereas here, the thousands of vehicles per day are on the y-axis. And it's the opposite for the sales. All right, so we get two scatter plots. We currently have these what we call density ellipses in red, which can be helpful for helping to visualize a trend. Sometimes, though, they can kind of be a bit misleading. So if you do want to get rid of those, that's an option using the drop-down menu. Okay. All right, so I'm looking at my scatter plot. It seems to be a linear trend. There is scatter around this imaginary line, but I don't see any curved patterns. So it does seem that correlation is appropriate here. So up in this little matrix here, we're going to have the correlations between all pairs of variables. Now, traffic versus traffic, they're the same number. So unsurprisingly, the correlation coefficient is 1. Same for sales versus sales. But the number that's important to us is where do those two variables meet? And they're going to meet in two spots. So we can either look at traffic versus sales or sales versus traffic. We're going to get the same correlation coefficient either way. So the value we get is 0.7407. All right. So I'm not going to worry about my little webcam. I guess you don't get to see any more of me today. Just listen to me. So there's our correlation coefficient. Now, what does that number tell us? So here's a scale. Now, this is a little bit arbitrary, but at 0 is no correlation whatsoever. As we go towards +1, the relationship gets stronger until it maxes out at the strongest it could be is +1 for the correlation coefficient. That would be if all your points were exactly on a line with positive slope. In the other direction, as we get away from 0 and go negative, at first it's a weak negative relationship, but as it grows closer and closer to -1, it's getting stronger and stronger. So the strongest negative correlation you could have is that all the points are aligned on a line with negative slope. Okay, so use that sliding scale to kind of figure out, is it a weak, a moderate, or a strong relationship? And then I have a little fill in the blanks for you to come up with quick and easy interpretations of your correlation coefficient. All right, so for the traffic example, we said we got 0.7407. And it's positive, there was no negative sign there. So we're right here on the sliding scale. So a moderately positive linear relationship. So that's what I would say. There's a moderately strong positive linear relationship between the traffic on the road and a gas station's sales. Right? Now notice I avoided using the word correlation in my interpretation because the point is to help explain what does this correlation represent to someone who may not be familiar with statistics. So if we were to use the word correlation in our interpretation, it would be like a circular definition. So stay away from that. So we'll talk about the strength and the direction of the linear relationship. Or you could say linear association. That would be all right as well. There we go. All right, so you give it a try. Use the other data set, the muscle data set. So find the correlation coefficient and try to come up with a one-sentence interpretation. Pause the video here while you do that. All right, so you should have found that there's a negative relationship between age and lean muscle mass, at least among middle-aged to elderly men. So here, the correlation coefficient is in red because it's fairly strong. And notice it's got a negative sign out front. So here we could say there's a strong negative linear relationship between the age of a man and his lean muscle mass, at least for men in their 40s through their 70s. All right, so that's going to be the most important part for us, finding the correlation coefficient and interpreting it. But it is important to keep in mind when correlation is not appropriate. So you may remember a month or so ago, we saw some data on the lakes in Florida. So if we plot the pH of the water on the x-axis and the chlorophyll concentration in the water, we see this sort of pattern. So notice it's not a generally linear trend. It doesn't go straight across like this. Rather, it kind of bends upward. So resist the temptation to find a correlation coefficient there. Or if someone gives you a correlation coefficient and doesn't show you the scatter plot, be a little bit skeptical, because it would not be appropriate here to say that there's a moderately strong linear relationship. Rather, it looks like a curvilinear relationship. Now, one thing we might be able to do to deal with a situation like that is to apply a transformation to one or both of the variables. So here again, we have pH for x, But if instead of chlorophyll, we took the natural log of the chlorophyll, an interesting thing happens. The curved pattern sort of straightens out. So now it does seem like the cloud of points more or less follows a linear trend. So there, it would be appropriate to say that there's a strong positive linear relationship between pH of the water and the log of the chlorophyll. Not the chlorophyll itself, though, because we saw that was a curved pattern. All right, so one of my figures disappeared. I will have to look for that. But if we were to add one more man to the muscle data set, let's say he's 75 years old and he has 110 pounds of lean muscle mass. Oh, now I can see it. Okay, here he is. So notice he is an outlier. He does not fit kind of within the cloud of points that everyone else fits. So if we include this person, the correlation coefficient drops rather dramatically to negative 0.6065. And compare that to the negative 0.8239 you should have got with the real muscle data set without that outlier. So notice that's a pretty big drop, and that's just due to one person. So that's another just thing to watch out for. If you're using correlation, it is pretty heavily influenced by outliers. So it'd be a good idea to check, if you have the means to do so, is this a legitimate value or not? Or maybe was this a typo? If you mixed up your digits, maybe it belongs over here with the rest. Then again, maybe this old guy is a bodybuilder. All right, and I am contractually obliged to tell you or remind you that correlation does not imply causation. So here's an example. Suppose that data is collected across the country, and for each county, like say Gloucester County, Camden County, etc., we get information on how many hours of exercise the residents get per week. Find an average for each county, and then what's the rate of skin cancer in that county? So we might find a strong positive correlation between those variables. And someone who's not statistics savvy might be inclined to think that that's indicative that exercise is bad, that it's somehow promoting skin cancer. So would it be appropriate to tell people to exercise less so that they can reduce their cancer risk? So what might be going on here? It might be that there's some what we call confounding variables or lurking variables, which are related with both of these things. So what might be related to both exercise and skin cancer? It might be exposure to the sun. So in certain areas of the country, like California or Florida, people who exercise might be doing more exercise outdoors. And if they're outdoors, they're being exposed to the sun and increase their risk of skin cancer. All right. So we wouldn't want to tell people to exercise less, that actually be bad for their health. But the kind of lurking variable was sun. So probably we should make sure that they're wearing sunscreen. Okay. So when you talk about variables that are correlated, we want to use some specific language to not overstate what we know. So we can say that there's a linear relationship or an association or even a link, because after all, we said, well, there is a link between skin cancer and exercise. It's just not a direct link necessarily. Okay. So unless it was data from a controlled experiment where, say, you control for people going inside or outside, we want to stay away from any words like causes, leads, or results, because those imply that one thing directly causes the other, which is not implied by the presence of a correlation. All right, so we've reached the end of the video. Now that you're familiar with the terminology, just make sure to go through this list and make sure that you're able to do all those things. And if you are, then you should be ready for part of the homework. See you in the next video.